All right, welcome to the next wind tunnel lab. Today we're going to be looking at the lift and drag on this cylinder. We'll take you in for a closer look so you can see it better in a second. But essentially we have a load cell here. This load cell measures in newtons. It's very, very accurate. So we have essentially 3 decimal places of newtons, so 1,000th of a newton, which is basically almost nothing, very, very small number. So we're going to have to be very careful with this tool because it's so sensitive. And then we have that attached to a plastic cylinder up here. And so we'll be running the wind tunnel at a bunch of different RPM, different wind speeds, and then finding the lift and the drag on the cylinder.
This load cell is set up such that it has 2 different settings. We can toggle those settings here with this little switch that you probably can't see in this view, but we'll show you in a second. If we toggle that switch upwards, it'll measure the lift force, which is how much that cylinder is literally lifting. And then the other one that we can look at is the drag force, and that one has to do with the opposition to movement. And so we'll toggle back and forth between these 2 switches throughout the lab procedure to get after both the lift and the drag forces under different flow rates. Great, so this is a close-up of the load cell. You can see here that newtons is labeled nice and large so that we can remember what units our force is being measured in. When this switch is toggled upwards, we will be measuring the lift force. We can also switch it downwards to measure the drag force instead. Like Dr. Stewart already said, this cell is really good and really sensitive to measuring different forces. It also has a lot of drift in it. So you can see while it's just sitting here, these numbers are changing even though we don't have any flow velocity going through the section whatsoever. And so we're gonna do a good job, or try our best, to continue to tear this device throughout the process. So we'll be turning off the flow in the wind tunnel, tearing it back to 0, putting the flow back on so that we do have a velocity in the section, and then taking a measurement. And even while I'm talking, you can start to see that the load cell is starting to drift from 0. So we want to make sure we don't have that offset from 0 when we start each measurement.
So this is a shot of the cylinder inside the wind tunnel. You can see that there is a brass post that the cylinder is attached to. The cylinder is acrylic, so you can actually see through it. And so, since it's a symmetric cylinder, it might be a little bit strange at first why we'd see any lift. And there are a couple different reasons why you'd actually see some lift. One is that it's not dead center in the wind tunnel. You can see that here. So we already showed in the last wind tunnel that actually the flow in the wind tunnel is pretty varied, and that is dependent on these flow straighteners here. So depending on whether the air is coming through one of the holes in the flow straighteners, or if it's on the weld, you get higher or lower wind speeds. So whenever you have a higher wind speed over, let's say, the top of the cylinder, and a lower wind speed over the bottom, that's how you're going to get lift. Anytime you have differential flow. Another source of lift could be from the post itself. So the post being on the bottom will actually slow down the flow going underneath the cylinder, and so then you might get some lift from that. But theoretically, if this were a perfectly uniform flow going over a uniform cylinder, we would see 0 lift. So one of the interesting things about this lab is that we can actually use the pitot tube and measure the flow in front of the cylinder. And so something that was sort of mind-blowing to me when I first learned fluids is that flow, when it approaches objects, actually knows that the object is coming, knows in quotation marks. So essentially there's pressure waves that go in front of the cylinder, and so the flow will actually slow down before it hits the cylinder. So you'll get a lower speed flow right in front of the cylinder before it gets there. So this is sort of interesting because if you think about supersonic flows, which I know are not in this class, but I always like to talk about this in the labs. So supersonic airplanes are shaped entirely differently than regular subsonic airplanes, like your passenger plane. So in your passenger plane, everything is pretty rounded and sort of, has the typical airfoil shape, but a supersonic jet is really pointy. The reason for that is that the pressure waves in flows that are telling the air in front to slow down, they actually travel at the speed of sound. And so when you're going faster than the speed of sound, the air doesn't know that the plane is coming when the plane hits and smashes into it. And so you get this sort of buildup of pressure waves. And if you ever take a graduate fluids course, they would talk about supersonic flows. So one thing that we can do to show the slowdown of the flow is just to take a velocity measurement in front of the cylinder. We can see that it actually will slow down as it approaches the cylinder. So the footage that we took of the different heights with the pitot tube didn't really come up very well, so I just wanted to do a quick sketch of what I was trying to get at, what it would look like if we actually were able to show that better. So you have your wind tunnel section like this. Your cylinder is going to be somewhere in the middle with the rod holding it up. And then if we looked at our velocity profile as a function of height with the pitot tube going down, we'd see the edge effect, so you'd have low velocity near the roof of the wind tunnel, and then it would speed up in this gap, but then slow down right in front of the cylinder, and then once again speed up here and then have edge effects. So if this is your flow, you'll actually see these two these two bumps where you have higher flow above and below the cylinder, and then of course the edge friction is going to have lower flow. So it's kind of hard to show in our wind tunnel because of the flow straighteners, so you end up getting these sort of jagged spikes like we saw in the last wind tunnel lab.